So here we're going to look at two examples, an easier one and a harder one to apply this method of initial rates. It's something you can see in free response. And when you do that, you need to be very complete in your explanations and justification, or very commonly in multiple choice, where we're just trying to look at it quickly and make some observations. So we have a reaction of NO with O2 reacting to make 2NO2. Important as we go through our results to remember that we're focusing on the data to make our rate law. So if we're looking for each reactant, we can choose either one to look at first. I saw, as I initially looked at the data, oxygen doubling and NO, nitrogen monoxide, staying the same in the first set. So that's the set I looked at first. When oxygen's doubled and the others held constant, so you can't just say in experiment 1 and 2, this happens. You need to, in a free response, be very specific and complete. When this chemical changes, holding all others constant, and it's good to refer to these, although not necessary. The initial rate goes from 7 to, or from almost 8 to almost 16. We could say that, or we could just recognize that it doubles, meaning that it is first order relative to that chemical that we just saw, which was oxygen, O2 to the first. Then we're looking for a scenario where that doubles and it stays the same. We could really pick a couple sets here, but we'll just look at 1 and 3. I double my NO, boom, my oxygen stays the same. And rather than going from 8 to 16, I go from 8 to 32. The initial rate quadruples. I stated what's changed. I stated what stayed the same. And then I said the results, which is second order relative to that. Right here is my rate law. That's often its own question if it is a free response. Obviously, that's might be the point of the question if it's a multiple choice. But here we're just kind of flowing through, recognizing what else we can do with it. If we want to know the value for K, we're looking at what we did before, plugging in a number here, our initial rate, and that means we're going to only use data from experiment 1. We don't know our K. We do know, and in this case, make sure that you're matching them up correctly with how you've written this. I, for whatever reason, put O first, or oxygen first, because that's the first data I dealt with. And then I did my nitrogen monoxide second. I've got my orders matched up, and then I get my value for K. Once again, sometimes small, sometimes big, a lot of times in between. If I want this side to be molarity on top and seconds on bottom, I'll definitely need a seconds on the bottom right here, which I have, but then I've got molarity, molarity, molarity. I only want one molarity, so really I have to cancel out the two molarities there, which is why there's one on the bottom, or excuse me, two on the bottom. A quick note, this one does happen to have a 2-to-1 ratio, and that's what works out here. That happens, but it is never the explanation nor the cause. So do not jump to that conclusion, or in a multiple choice, lean towards that over something else. When it finally asks what's the initial rate here, we've got two new scenarios. We're still talking about the same temperature unless it gives us something different. So we can use the same K, plugging these in, once again, making sure they're in the right places. And it looks like I did this wrong. So I'm going to double check while I pause it here, but I'm going to keep the video rolling because I'm doing a great job. And we've magically fixed it, and it was never wrong on yours to begin with. So we're good to go. As we come down to B here, we've got a little bit more complex looking reaction, at least in terms of some of the ions. The peroxydisulfate ion, iodide, making these things. So we've got our numbers, we've got some rates, and we're going to check this one out. When S2O8 2- increases from this to this, that's 1.48 times more. It's 1.5 times more while holding the other reactant constant. The initial rate does not change. So that means the reaction's zero order right there. So one thing that's important is that's a weird fraction, but we recognize that however weird that fraction or that increase is, doesn't actually matter. So that's good to know. Well, iodine here does increase by a fraction that's more familiar or easy. It doubles. The other thing's held constant. And the initial rate goes from zero point 0.2 to 2, or it's 2 divided by that. It is 8 times faster. That means that it's third order. So doubling something makes it go 8 times faster. That's 2 times 2 times 2, 2 to the third power. So when we put this together, we've got the rate equals K, this to the 0. You can always keep that in, but it's also important to remember that that means the concentration of S2O8 2 minus doesn't impact the rate. So we can do it a little more simply here. We can put in a rate, we can put in a value here, so we can match that up. Obviously, experiment 1 and 2 are both the same there. We cube that, we get our value here. We've seen some that are decimals, some that are big numbers, and here we're just kind of like a small double-digit number. Our unit, once again, is canceling out some of our molarities. Because this was per second, we've got the second there. As we think about this, a great follow-up question, multiple choice free response connecting from one part to the next. When it's tripled, what happens? Well, 3 to the third, 3 times 3 is 9, times 3, it's 27 times faster because it's third order. Oh, sorry. And then this last part here connects all the way back to what we started with in our first videos. If we're thinking about how much of something is consumed, it is stoichiometry. So even though we defined this is zero order and we don't think of orders in terms of our products, we still have a 1 to 3 to 2 to 1 ratio. The rate law tells us how the amounts speed up and slow down the reaction, but they are still being consumed in that ratio. So we have a certain amount of iodine, how much is consumed in terms of sulfate, or how many sulfates are produced, Well, there's 2 sulfates produced for each 3 iodines, so we will make that much. So just remember that as we talk about rate laws, we don't necessarily jump straight in. Yes, this was a 3, another somewhat of a coincidence there because I wanted to make sure I had a third order reaction. But that one, actually, it didn't match with the coefficient, but the coefficients are not totally ignored. They are valuable for relative rates.